Thank you for letting me go out of order, I guess. Talking about expander constructions. My co-authors are Valentin Kabinets, Antonina Kolikolova, and Michal Kuski. Let me start with the outline of the talk. I'm going to, of what's in the talk. First of all, we discuss a combinatorial construction of expander graphs, which has proofs of correctness that avoid algebraic concepts such as eigenvalues. This will bring the construction down to something that can be carried out in NC1, including all the proofs only use things that are in NC1. This I'll discuss very briefly, means it can be formalized in a first order theory of arithmetic called VNC1. And from that, there's a correspondence between VNC1 and polynomial size formulas. And then we use that to get a polynomial simulation of monotone propositional logic, of propositional logic by monotone propositional logic. This is the outline, parts 1 through 4. Good. So I have a lot of material for the talk, but I'll stop in 20 minutes, but might as well ask questions as I go along anyway, and rather than saving them for the end. Okay, so first of all, I think everyone knows what expander graphs are, but please take a quick look at the slide and refresh it. These are well-connected graphs. I'll define it in a moment. They have the properties that random walks converge quickly to the uniform distribution. They have many applications. In particular, for us, the AKS sorting networks are constructed using expander graphs, and that's what we really depend on in our talk here. Okay, so the definitions. Here I've got a constant degree D for my graphs, and an expansion property is what's given here. We say the edge expansion is you take a subset U and its complement U bar. It should be a proper partition of the set of vertices. You look at the number of edges crossing between U and U bar and divide it by D times the minimum of the size of U and the complement of U, and that's the so-called edge expansion. The edge expansion of the graph G as a whole is the minimum over all such choices of subsets of vertices U, and it's an expander graph if the edge expansion is some constant bounded away from 0. The subscript D, or the D in the denominator, is just a sort of normalized by the possible number of edges that could be crossing the boundary. The traditional proofs of this, of course, we know if we take a random graph, we have edge expansion. That was the first proof of the existence of expanders. The traditional proofs of constructive of expanders are based using the second largest eigenvalue and the spectral gap, and we'd like to avoid that in these constructions. Okay. And the usual construction due originally to Reingold, Wadhan, and Widgerson was based on the following type of methods. You do graph powering. Graph powering means you take short paths in the graph and treat those as new edges. The zigzag product or replacement product, which is, I'll talk about that in a moment, but you replace the vertices of the graph with another small graph, are used to reduce the degree of the graphs. Tensoring is used to increase the size of the graph. Adding self-loops is done for technical reasons to maintain the edge expansion. And the original proofs used spectral gaps. We're going to use a couple techniques from subsequent proofs. The replacement product is something similar to the zigzag product, and it was proved to be correct with a combinatorial argument that avoided the spectral gap. And we're also going to use Michal's combinatorial proof of mixing times for handling powering. And the net result is we have an NC1 algorithm for defining expander graphs, in particular defining rotation maps. Okay. Here's the little more detailed description of the construction that we use. We start with constants C and D, positive integers, and two small graphs that can be found by brute force. A 2D regular graph G sub 0, which has positive edge expansion greater than 1 over 1,1296, and a D regular graph H with edge expansion greater than 1/3. And D can be some small number like 6 or something like that. Okay. We then, having gotten G0, we construct G1, G2, et cetera, by the following process with this rather complicated formula here. We add self-loops, so we add D self-loops to every vertex, which doubles the degree. We tensor the result with itself. We raise to the power, we add self-loops again. We raise to the power C, and we replace each vertex in the resulting graph with a copy of the fixed graph H. Okay, and this then, that's the replacement product of the small o. And this has the effect of building this. The theorem then is that this gives us another graph. If GIs, each GI has edge expansion at least epsilon. Epsilon is this fraction 1 over 1296. The size of GI plus 1 is actually bigger than the square of the size of GI. The exact formula is given here. But basically, you should think of the size of the graph G sub I as being 2 to the 2 to the I. Every time we iterate this, we square the size of the graph. Okay, so, all right. So that's the basic construction. And what's important about it is that we can prove its correctness using only concepts from NC1. Okay. So for this, we really want to talk about the rotation map. The rotation map, if I dare write on the board, is if we have a vertex V with a lot of edges, and we look at the jth outgoing edge, the rotation map gives us the neighboring vertex K along that edge, and the neighboring vertex W along that edge, and the index K of the edge from the point of view of W. So the rotation map is just a way of walking around the graph. And the main theorem here for the construction is the rotation map of G sub I is uniformly computable from I, J, and V in either polynomial time or separately in alternating linear time. Okay. So to be precise, what this means here, I, J, and V are integers, and how big are they? They're logarithmic in the size of G sub I. So remember, G sub I had size about 2 to the 2 to the I. So the length of V is approximately just 2 to the I, right? So the number of bits needed to specify the vertex V is logarithmic in the total size. And I'm saying it's polynomial time, for instance, in the size of the vertices, not in the size of the graph here, right? Okay, and it's alternating linear time in the size of the specification of the vertices, not in the size of the whole graph. So that's the same as alternating log time in the size of the whole graph. Okay, so the proof of the main theorem, I'm going to wave my hands very much over this. First of all, just a straightforward unwinding of the construction from the previous slide gives us a polynomial time algorithm. For alternating linear time, it's a little trickier, but basically you show that with constantly many alternations, you can answer questions about the rotation map for G sub I plus 1, given an oracle for questions about the rotation map for G sub I. So again, we can reduce the questions about the rotation map for G sub I plus 1 to questions about the rotation map for G sub I. And that can be done in alternating linear time with a constantly many constant alternation linear time. Now the second part of this then is that the GIs, each one is GI plus 1 is the square of its size is bigger than the square of the size of G sub I. So the specification of vertices is shrinking in half from GI plus 1 down to GI. So if you unwind these recursive calls, you have linear time, and then you've got basically half linear time, and then quarter linear time, and so forth. And so the overall runtime is still linear time, but no longer constant alternation. And that's the idea of the construction. Okay. All right. You can ask questions if you want to, but I'm going to keep going unless you jump up. Okay. So as a corollary, I should say then, because of the way where the correspondence between the graph is exponentially bigger than the indices for the vertices, we get an alternating time algorithm, a uniform NC1 method for computing the edge relation on G sub I. So the other thing we need is not just a construction that can be carried out in NC1, but we want the proof of correctness to be carried out in NC1 as well. And so what was the proof of correctness is going to be? The proof of correctness is going to have to say that give me any subset U of vertices, there better be a lot of edges coming out of it. So the way the proof of correctness goes is if I have a subset U of vertices for GI plus 1 that does not have enough edges coming out of it, then I can build a subset U prime for GI that doesn't have enough edges coming out. And there's an NC1 method of given an oracle for U, you can find U prime in alternating log time, right? Giving oracle access to the members of U. You can compute the membership relation on U prime. Okay, I'm not going to do the proof, but that's what's needed here. So this is what I mean by an NC1 provably correct expander graph. A little puzzled, but okay. But I'll keep going. Okay. So this kind of argument can actually be formalized in formal theories of arithmetic. So I realize probably the number of people in the audience who've studied bound arithmetic is zero if you don't count me. So
highly bounded.
Highly bounded, sharply bounded. So we're okay. But nonetheless, so just to say there's been a fairly long line of work, but the theory I'm interested in here is what's known as VNC1, due to Steve Cook and Morioka building on earlier theories of especially Arai. And it has the property that the arguments that can be carried out are precisely the arguments can be formalized using concepts from NC1. Okay, so I'll just stop there and say that. But so basically, VNC1 can carry out the kinds of arguments needed for the omitted proof of this lemma, for instance, here in the previous theorem. Okay, and the kind of constructions that are needed are sort of simple combinatorics, counting, like counting the size of a set of vertices, and adding up series. And adding up series is adding up polynomially many things. This can be done with polynomial size formulas using, say, carry-save addition from classic results from the early 60s with NC1 formulas. All these things and their properties can be proved in VNC1, and it can carry out the entire argument from the previous slides. Okay, and to give a little more detail here, but not much more, first order, so VNC1 deals with first order objects and second order objects. First order objects encode things like vertices, indexes, and edges as pairs. Second order objects encode sets, which is sets of vertices or sets of edges, that is to say graphs. And so then you get this sort of theorem here that says VNC1 can prove a statement like for every first order index I, there is a set G of vertices and edges which has the right size and has the right edge expansion. And all that kind of stuff can be done in VNC1. Okay, so skipping past the set of size 0, who knows bounded arithmetic, let me come to the final stage of the talk, which is monotone Boolean formulas. So, okay, we're back on, if your eyes glazed over a little bit, you're all back on familiar ground again. Let's order true and false, so false is less than true. Function is monotone. We've already heard about this from an earlier talk. If whenever a vector, the inputs x are less than or equal to the inputs y, we have the output f of x is less than or equal to f of y. A monotone Boolean form, blue screen of death. That's not good. Let me see, it says it's rebooting. 40% complete. It's a very blue thing with a 60% on it. Anyway, let me just say it. We have a monotone Boolean formulas are ones that use ands and ors and no negation signs. And we want to talk about tautologies formed from monotone formulas. So what I mean by tautologies formed by monotone formulas is, of course, tautologies can't be purely monotone because if they only involve and ors, you could just give them false inputs and the output is false. But instead, how is that? My computer is getting better and better at rebooting with practice. It's the third time today. So since you can't form tautologies out of monotone formulas, you can instead look at monotone formula implies monotone formula, where A and B are both monotone, and ask, is that a tautology? Hold on. Where am I? Okay, you can hold on for another 2 or 3 minutes, right? Okay. Blue circle. Okay, so you can look at monotone formulas imply, I've got a blue circle going, it's going to do it again. Monotone formula implies monotone formula. So for instance, a good example is the pigeonhole principle. It's just that's the still booting blue circle. Aha. perfect. No, I'm not. No, I don't want to turn on sticky keys. Ta-da. So for a good example is the pigeonhole principle. You can take the conjunction over all n+1 values of I, disjunction over j, some xij is true, where there's only n values of j, then there's some place where the pigeonhole principle is violated. So this is a perfect example of a monotone tautology. Okay. Classic, well, I have to first make sense. So the propositional sequent calculus works with monotone formulas. We have a set of formulas. A sequent has a set of formulas implies a set of formulas. It means the conjunction of these formulas implies the disjunction of these formulas. And so the lines all have the form formulas imply formulas. For propositional logic LK, we allow not only monotone formulas, but also non-monotone formulas. And we have general rules like the cut rule and the and right. And a classic result, I suppose, is that the pigeonhole principles have polynomial size LK proofs where you allow non-monotone formulas in the proof. The monotone sequent calculus is the same thing, except you restrict to having only monotone formulas appearing anywhere in the proof. And we do allow, technical point, we do allow monotone LK proofs to be DAG-like, not just tree-like. Okay. Very nice result from now 15 years ago or so is that the monotone LK system quasi-polynomially simulates LK. So as a corollary, the monotone sequent calculus has quasi-polynomial size proofs of the pigeonhole principle tautologies. And their proof was based on, they used slices. So we say if you knew there were exactly I inputs are true, to say that not X holds, you would say that I other variables are true. Okay, and so essentially lets you say not A. So you say, oh, what about the case where exactly I inputs are true, and you handle that case separately from all the other ones. So that way you can express negation by just saying that enough of the other things are true. Very hand-wavy proof. In particular, they needed threshold functions to do negations. And the natural threshold functions had quasi-polynomial size if you do a divide and conquer thing. On the other hand, we know that AKS sorting networks give us polynomial size monotone formulas, and they're built with expander graphs. And Emil Urabek earlier, about 5 years ago now, proved that if the VNC1 can prove the existence of expander graphs, then MLK polynomially simulates LK. He actually worked with a slightly different system, but it works for VNC1 as well. So as a corollary to his theorem and our theorem from a few slides ago, MLK polynomially simulates LK. And says, for example, a sample corollary then is MLK has polynomial size proofs of pigeonhole principle tautologies. How am I doing on time? 1:40 minute and 45 seconds left. Good.
You can do a little extra.
I can do a little extra. Thank you. Okay. Well, actually, I don't need to do much extra. So one thing here is that I know probably most people in the room have studied the AKS construction before. Probably remember this with great dread because it was a terribly complicated construction. So you take the expander graphs and you put them together in very complicated ways and you build a sorting network. And it was log many rounds that work, but it was a very complicated way of putting these things together. And it turns out that these are log space uniform circuits, but it's open whether they're, so the direct connection language of these circuits, as it's called, is recognizable just in log time, in fact, but I'm sorry, in log space. But the extended connection language, which is to say if I give you a node and a short path in the circuit, where do I end up with? That is not recognizable so easily. So that's an open question, which I'll say here is coming to the second open question here is, are there, forget provability for the moment, are there E star uniform sorting networks? So can you put together these expander graphs, which are very uniform, into uniform sorting networks? So in particular, we have the expander graphs now that can we modify? Can we also get the AKS to be uniform? So in particular, can the monotone LK system polynomially simulate the LK system with an alternating log time construction of the simulation? Another open question then is, do we need really the full power of NC1? Would TC0 be enough? Can we define expander graphs using just TC0 uniform methods instead of NC1 uniform methods? The technical question is, can the tree-like MLK simulate MLK? That's an open question. And it's flashing
Your
red.
time is out and your laptop is out, so I think.
My time? Oh. Well, I'm out. Okay. All right.
Leland?
Yeah.
No questions, please. Sorry.
There was something there about formalizing USTCon.
It flashed away, yes.
Yeah,
So,
can you comment on that? That looked intriguing.
right, so USTCon, undirected STCon activity, would be nice to know, can you formalize this in a system that can formalize log space reasoning? Or even, I don't think it's even open for NL reasoning as well. So, yeah, that would be nice, you know. There are weak formal systems of arithmetic there that could formalize undirected STCon activity results, but we don't know how to do that yet, right? Yeah. Does that answer your question?
Would that have consequences for like the strength of a proof system that you need to de-randomize to prove RL equals L?
Yeah, so that would be, right. So for instance, where can you prove RL equals L, for instance? Okay. Seems to me, there's a lot of, I haven't looked at those questions for a while, but there's a lot of, you know, SL is closed under complement would be another one of these kind of things. Where is this provable? I think that's open. And there are systems, there's V1 sim crom corresponds to SL reasoning due to Antonina. There are systems out there that do those things, okay. Yeah.
Let's take further questions offline.